May this video wash away the fatigue of your busy day. Sit back, relax, and enjoy a quiet moment. May you have a beautiful dream tonight. Do you believe the universe is infinite? Scientists may have discovered a secret that could change everything. Imagine two trains racing along parallel tracks, chasing each other, exchanging the lead. Spectators cheer from the platform, waving flags, rooting for their favorite train. But then, something unthinkable happens. The trains collide. Metal folds like paper. Flames erupt. But how can that be? The tracks are parallel. And by definition, parallel lines never intersect, no matter how far they stretch. So how can two trains on parallel tracks crash? Mathematicians have studied parallel lines for thousands of years. The Greek scholar Euclid, often called the father of geometry, wrote one of the most influential books in history, The Elements. In it, he laid out the foundational rules of geometry. Among them was the fifth postulate, the parallel postulate, which essentially states that two parallel lines will never meet. The other four postulates were easily proven, but the fifth remained elusive for nearly 2,000 years. In the 19th century, mathematicians finally dropped a conceptual bombshell. The parallel postulate couldn't be proven, not because it was false, but because it wasn't the only possibility. Under different assumptions, parallel lines could indeed intersect. Euclidean geometry was no longer the only truth. Non-Euclidean geometry emerged. Space itself could bend, twist, and warp, completely rewriting the rules. Hungarian mathematician János Bolyai and Russian mathematician Nikolai Lobachevsky were among those who introduced this new way of thinking. Suddenly, geometry became flexible. And surprisingly, this change didn't stay in the realm of abstract mathematics. It became central to our understanding of reality. Why does this matter beyond math? Because today, non-Euclidean geometry lies at the heart of our most fundamental theories about the universe. It leads us to one of the biggest questions in modern cosmology. If the universe is expanding, what is it expanding into? Our journey will take us into a strange, warped cosmos, where light can loop back on itself, where the same galaxy can appear multiple times in the sky, where space folds in such a way that if you look far enough, you might even see yourself looking back. A universe where parallel lines can intersect again and again. This will be a journey that challenges our intuition, but one that may bring us closer to understanding where and what we truly are. In the Middle Ages, a man named Robert Grosseteste made a remarkable early contribution to science. He was the first to correctly explain rainbows as a result of light refraction. Light became his lifelong fascination, and in his cosmological model, it played the central role. According to Grosseteste, the universe began from a single point of light that expanded outward and condensed into matter. This idea predated the modern Big Bang theory by more than 7 centuries. Today, some even call him the Bishop of the Big Bang. He died in 1253. In 1927, Belgian priest and physicist Georges Lemaitre published a solution to Einstein's general relativity equations, our most complete and accurate theory of gravity. Unlike previous interpretations, Lemaitre's solution suggested that the entire universe was expanding. Most ignored him. Einstein himself was critical, famously saying, "Your calculations are correct, but your physics is atrocious." He even modified his equations to preserve a static universe. But the seed of truth had been planted. In 1915, American astronomer Vesto Slipher observed that galaxies appeared to be moving away from us. He discovered this using redshift, the stretching of light waves as galaxies recede. By splitting starlight into its spectrum, identifying absorption lines, and measuring how far those lines shifted toward the red end, he calculated the speeds at which galaxies were fleeing. But that was only half the puzzle. In 1929, Edwin Hubble added the missing piece. He measured the distances to these galaxies and compared them to their redshifts. The farther a galaxy was, the faster it seemed to be receding. This correlation became known as Hubble's law. According to modern measurements, galaxies recede about 23 kilometers per second for every million light-years of distance. Hubble immediately understood what this meant. Lemaitre had been right. The universe was expanding, just as Grosseteste had once imagined. Although people often talk about it, it's not always immediately clear why the fact that more distant galaxies appear to move away faster implies that the universe must be expanding. So let's use a more familiar example to explain this connection. Raisin bread. Imagine mixing and kneading dough filled with raisins, then placing it in the oven to bake for an hour. During that time, it doubles in size, giving you a delicious treat. Now imagine shrinking yourself down and placing yourself on one of the raisins. As the dough expands, what do you see? A raisin that was 1 centimeter away from you will, by the end of baking, be 2 centimeters away. It moved 1 centimeter in an hour. A raisin that was 2 centimeters away will now be 4 centimeters away, moving at 2 centimeters per hour. A third raisin, 3 centimeters away, ends up 6 centimeters away, 3 centimeters per hour. In other words, the farther a raisin starts from you, the faster it appears to move away. Why? Because the dough is expanding. The raisins aren't moving through the dough, and no new dough is being added. Instead, the space between them is stretching. The more dough there is between you and another raisin, the more expansion stretches that distance. Hubble's law tells us the same thing about galaxies. As Vesto Slipher observed, most galaxies appear to be moving away from us. But the galaxies themselves are not flying through space. Rather, space itself is expanding between them. The farther a galaxy is, the faster it appears to recede. Not because it's moving faster, but because there's more space between us that is stretching. No new space is being created. Existing space is being stretched. This is allowed in general relativity, where space and time are flexible, not fixed. This expansion also explains why light from more distant galaxies shows greater redshift. As light waves travel toward Earth, they are stretched by the expansion of space. Among all the colors of the rainbow, red light has the longest wavelength. The more space light travels through, the more its spectrum shifts toward red. This also sheds light on another question that often puzzles people when thinking about an expanding universe. What happens to energy? Energy conservation is one of the most famous principles in physics. It states that energy can neither be created nor destroyed. The total energy in a system must remain constant. But in an expanding universe, energy is not conserved. Newtonian physics assumes particles move through a fixed background of space. But in an expanding universe, space itself changes. As a result, the total energy of particles moving through it doesn't remain constant. Redshifted light is a great example. As light waves are stretched by cosmic expansion, they lose energy. The total energy of photons arriving at Earth is less than when they were emitted. It hasn't been transferred elsewhere, it simply no longer exists. That's the cost of expansion. The expansion of the universe also causes another strange effect. Light from the oldest events in the universe takes longer to reach us because it must travel across an expanding space. As a result, the oldest cosmic events we observe appear to evolve nearly 5 times more slowly than similar events today. So the universe is clearly expanding, but when did that expansion begin? If the universe is larger today than yesterday and smaller a century ago, we can rewind the expansion. Hubble's law allows us to do just that. If we reverse the expansion far enough, we find that all of modern space was once compressed into an infinitely small point. Lemaître called this the primeval atom. Today, we call it the Big Bang. Reversing Hubble's law tells us the expansion began around 13.8 billion years ago. The name Big Bang may suggest an explosion, something that happened at a specific point in space. Understandably, people ask, where did the Big Bang happen? If a bomb goes off in a room, investigators can analyze debris and pinpoint the blast's origin. Why not do the same for the universe? The problem is, the Big Bang didn't happen in space. It created space. If the explosion created the room itself, asking where it occurred within that room is meaningless, because there was no room before it. In an expanding universe, everyone sees themselves as the center of expansion. But in truth, there is no center. The universe didn't expand from a place, it expanded from a state. That leads to the next question. What is the universe expanding into? This is one of the most frequently asked and surprisingly difficult questions in cosmology, and it profoundly affects how we understand the very shape of the universe. When flying low across the surface of the moon, you witness a vast, monochromatic landscape. Prehistoric craters, smooth lava plains, towering mountains, and delicate rills that stretch as far as the eye can see. For billions of years, this ancient desolation has been touched by only 12 human footprints. To skim across the moon's jagged terrain is not only to witness alien beauty, but to fly through the history of science itself. There, etched into its surface, are the names of those who once gazed into the sky and asked, "What is space? What is time? Where does it all lead?" Among them, one name appears again: Einstein. Hubble, Slipher, and Lemaitre have all left their mark, not only in science but even on the moon. 2 lunar craters on opposite sides of the moon are named after them, one in the near side's northern hemisphere, the other in the far side's southern half. Their physical opposition is fitting, because the scientists they are named after, Willem de Sitter and Hermann Minkowski, also proposed opposing possibilities for the shape of the universe. Which one turns out to be correct could determine whether the universe will one day end, and what it truly means when we ask, what is the universe expanding into? Minkowski was once Einstein's professor, though they didn't always see eye to eye. Minkowski once called Einstein a lazy dog who didn't care about mathematics. In truth, Minkowski was closer to the legendary German mathematician David Hilbert. Willem de Sitter, born in 1872 into a family of lawyers, abandoned law to pursue the hidden rules of the cosmos. When he died of pneumonia in 1934, the New York Times described him not as a cold manipulator of Greek letters or a technician of balanced equations, but as an artist, someone whose formulas sang and whose vision of the universe could only be fully appreciated by musicians. Both men are remembered for their work on the overall shape of the cosmos. Minkowski space and de Sitter space are different ways to describe how the fabric of the universe might bend. Minkowski space is what physicists call flat, although that name can be misleading. In mathematics and astronomy, flat doesn't mean two-dimensional like a sheet of paper. It means the space has zero intrinsic curvature. And as we'll see, many shapes can be flat while still being fully three-dimensional. In Minkowski space, geometry follows the rules of Euclidean mathematics, named after the ancient Greek Euclid. You may not recognize the term Euclidean geometry, but it forms the foundation of high school math. In Minkowski space, triangles always add up to 180 degrees, and parallel lines never meet. That's what your math teacher probably told you. But what they may not have told you is that this doesn't hold true for all triangles. To see why, let's return to the moon. Imagine standing at the moon's north pole. You walk south toward the equator, passing by the de Sitter crater. At the equator, you turn 90 degrees and walk a while. Then you turn another 90 degrees and head back to the North Pole. Your path traces out a triangle across the rugged lunar surface. But this triangle already has 2 90-degree angles at its base, and the third angle at the pole isn't 0. That means the sum of the angles in this triangle exceeds 180 degrees. In fact, on a sphere, triangle angles can add up to as much as 540 degrees. This is an example of non-Euclidean geometry. A universe with this kind of shape is called closed, like the surface of a sphere. Even if you walk in a straight line, you eventually return to where you started. This positively curved space is known as de Sitter space. But there's also a third possibility, anti-de Sitter space. In this kind of geometry, triangle angles sum to less than 180 degrees. That's due to negative curvature, like a saddle or a Pringles chip. Such a universe is called open. The curvature squeezes the triangle's corners, reducing the total sum of their angles. So among these 3 options, which universe do we live in? Open, closed, or flat? Imagine a spacecraft tracing a giant triangle across the sky. It travels millions of light years, then returns to Earth. This is the same idea as drawing a triangle on the moon, just scaled up. If it takes more than 180 degrees to close the triangle, the universe is positively curved. If it takes less, the universe is negatively curved. Only if it takes exactly 180 degrees is the universe flat. Unfortunately, no astronaut has ever gone beyond the moon. Even our most distant spacecraft would take tens of thousands of years to reach the nearest star, let alone escape the Milky Way or travel millions of light years in pour. Luckily, there's something else that has traveled across billions of light years. Light from the cosmic microwave background, the afterglow of the early universe. When we map the cosmic microwave background, we find tiny temperature variations. These correspond to regions of the baby universe that were slightly more or less dense. The denser regions would grow into vast galaxy clusters. The emptier ones would become enormous cosmic voids. Using Hubble's law and our understanding of the expanding universe, astronomers can work backward from today's cosmic structures to predict how large these early patches should appear. The results match the data perfectly. This tells us that light from the cosmic microwave background has traveled through a flat universe, a universe governed by the rules of Minkowski space. Next, astronomers must determine the universe's topology. Keep that word in mind. We might dedicate an entire episode to it. But to get a sense of what topology means, imagine two objects made of clay. If one shape can be transformed into another without tearing or cutting, they are said to have the same topology. For example, a donut and a teacup are topologically equivalent. The hole in the teacup's handle can be reshaped into the donut's central hole. No cutting is required. The universe itself might follow a similar logic. Imagine the universe as a giant sheet of paper. If you roll the sheet, you get a cylinder. If you then connect the ends of the cylinder, you form a torus, what we call a donut. Mathematicians refer to this as a three-torus. Interestingly, all of these shapes are considered flat because any triangle drawn on their surface still has internal angles that add up to 180 degrees. They obey Euclidean geometry. In fact, there are 18 possible three-dimensional topologies that are consistent with a flat universe. The simplest is the infinite plane, a universe that stretches endlessly like an unrolled piece of paper. In such a case, the universe is infinite, and its expansion cannot occur by occupying more space because it already contains all the space there is. But is the universe truly infinite? Some alternative topologies that are consistent with cosmic microwave background observations and a seemingly flat universe suggest otherwise. Imagine an ordinary cube. Now bend and connect each pair of opposing faces. Do the same with the remaining pairs. The result is a finite 3D torus, where traveling in a straight line could eventually bring you back to where you started. Other topologies, such as the Hahn-Vent manifold, begin with two connected cubes and twist space in even more complex ways. If the universe has such a shape, we might live inside a cosmic kaleidoscope, where light traveling along closed loops could allow us to see the same object multiple times in different parts of the sky. Astronomers have searched the cosmic microwave background for repeating, matched patterns that would indicate such loops, but no clear matches have been found. One reason might be that some topologies, like the Hahn-Vent manifold, are so complex that their repeating patterns are hard to detect. To make matters more complicated, astronomers aren't even 100% sure the universe is truly flat. This uncertainty is known in cosmology as the flatness problem. Astronomers can measure the geometry of the observable universe using the cosmic microwave background, but what lies beyond that boundary remains unknown. Two competing possibilities arise. Either the entire universe is flat, including the part we cannot see, or only the observable part appears flat, because cosmic inflation smoothed out its curvature. It's similar to how Earth looks flat beneath your feet, even though it's curved. The curvature becomes noticeable only on much larger scales. In the case of the universe, those scales may lie beyond what we can observe. But there's a problem. Hubble's law tells us the universe has only been expanding for about 13.8 billion years. That's not enough time to fully flatten all observable curvature. The most widely accepted solution is cosmic inflation. According to this theory, in a fraction of a second after the Big Bang, the universe underwent a brief period of extreme, superluminal expansion, faster than anything Hubble's law describes. This inflationary period also explains the tiny fluctuations we see in the cosmic microwave background, fluctuations that shouldn't exist in the original Big Bang theory. Inflation predicts they arose from quantum ripples, frozen in place as the universe expanded rapidly. But so far, there is no direct evidence that inflation actually occurred. Finding such evidence would reframe how we think about the shape and finiteness of the universe. Still, it raises the familiar haunting question: what is the universe expanding into? Surprisingly, the answer may be nothing at all. The universe might not need to expand into anything. Let's rewind to the 1780s. America was still in its infancy. France stood on the brink of revolution. King Louis XVI would soon face the guillotine. Meanwhile, in Germany, a young student named Carl Friedrich Gauss sat quietly in a classroom. His teacher had just assigned a task: add up all the numbers from 1 to 100. Within seconds, Gauss announced the answer: 5050, sir. His teacher's jaw dropped, perhaps more sharply than the guillotine's blade. Whether or not this story is true, it has become one of those famous tales of scientific legend, like Archimedes running naked through the streets, or the apple falling on Newton's head. The trick, of course, is that Gauss didn't add the numbers one by one. He noticed a pattern. 1 and 100 make 1 and 1, 2 and 99 also make 101, and so on. With 50 such pairs, he simply multiplied 101 by 50 to get 50/50. Whether or not the story is true, its purpose is to illustrate one thing: Carl Friedrich Gauss exhibited extraordinary mathematical talent even as a child. He would go on to become one of the most influential, if not the greatest, mathematicians in history. His work ultimately became foundational to our understanding of the universe, particularly what it means to say the universe is expanding, and whether it needs to expand into anything at all. Earlier, we used the raising bread analogy to explain the expanding universe. Another popular metaphor is that of coins pasted onto the surface of a balloon, representing galaxies. As you blow up the balloon, the galaxies move apart as the space between them stretches. Likewise, we don't expand along with the universe. Our atomic bonds hold us tightly together. Yet all these everyday analogies have limitations. In both the raising bread and balloon cases, the objects are expanding into something: a room, an oven, an external space. To truly understand how the universe can expand without expanding into anything, we must turn to a more abstract and often counterintuitive branch of mathematics: differential geometry. First, imagine a two-dimensional sheet of paper being rolled into a cylinder. To do this, you must bend the sheet through a third spatial dimension, something beyond the paper itself. Mathematicians call this external dimension the embedding space. Now, suppose our universe were actually shaped like a cylinder. A brave astronaut could chart a giant triangle on its surface, and the triangle's internal angles would still add up to 180 degrees, just as they did on the original flat sheet of paper. From the astronaut's point of view, they would not be able to tell whether they were on the flat sheet or the curved cylinder, unless they could leave the surface entirely and look back from the embedding space. Only then would they see its curvature. Shapes like this are said to have extrinsic curvature visible only from outside the surface. In contrast, a surface like a sphere has intrinsic curvature. You don't have to leave the surface to know it's curved. On a sphere, the angles of a triangle can sum to more than 180 degrees. That tells you the surface is curved from within. This idea, curvature that can be measured from the surface itself, was formalized by Gauss in 1827. He called it theorema egregium, Latin for the remarkable theorem. One consequence is that any attempt to project a three-dimensional sphere onto a two-dimensional map will always introduce distortion. The familiar Mercator projection preserves angles for navigation but distorts size. Greenland appears 14 times larger than it actually is. Other projections, like the Lambert cylindrical equal area map, preserve area but distort angles. Gauss's theorem proves there's always a trade-off. So far, we've been discussing hypothetical cylinders, spheres, and maps of Earth. But what about the real universe we live in? At 76, Gauss attended a lecture by his former student, Bernhard Riemann. Born the year before Gauss published his remarkable theorem, Riemann initially intended to study theology at the University of Göttingen under Gauss's supervision. But he eventually switched to mathematics. Gauss once said Riemann had a brilliant originality. In an 1857 lecture, Riemann expanded Gauss's work in differential geometry beyond 3 dimensions. Today, this branch of mathematics is called Riemannian geometry. As we'll soon see, it was a critical breakthrough. One of the most important concepts in Riemannian geometry is the geodesic, the shortest path between 2 points on a curved surface. This can lead to some unintuitive results. Take the example of flights between London and New York. London is farther north than New York, so you might expect a plane to head southwest. In reality, it heads northwest, flying over Greenland, along a geodesic. On a two-dimensional map, this looks like a curved arc. But from space, you can see it's actually the straightest path. Even more curiously, you can fly from Alaska to India without crossing land. On a flat map, this path looks anything but straight, but from above, it's clearly the shortest. These ideas, geodesics and Riemannian geometry, became the mathematical foundation of Albert Einstein's general theory of relativity, our best theory of gravity. General relativity states that three-dimensional space and one-dimensional time are interwoven into a four-dimensional structure called spacetime. In fact, the term spacetime was coined by Einstein's mentor, Hermann Minkowski. This meant that Gauss's differential geometry, limited to 3 dimensions, was no longer enough. Only Riemann's generalization to arbitrary dimensions could describe the full geometry of the universe. According to general relativity, the presence of mass causes the four-dimensional spacetime to curve. For example, Earth doesn't orbit the Sun because of some invisible force, as Newton once suggested. Instead, Earth is following a straight path, a geodesic, through a curved spacetime created by the Sun's mass. Instead of orbiting the Sun due to an invisible force, Earth rolls along the curves of spacetime, distorted by the Sun's mass. This way of thinking about gravity leads to a rather counterintuitive claim. Earth moves in a straight line, at least in four-dimensional spacetime. Much like how a straight flight path from London to New York appears curved on a two-dimensional map, Earth's straight path through curved spacetime looks like an orbit when viewed in 3 spatial dimensions. This curvature is especially dramatic in gravitational lensing. When light from a distant galaxy passes near a massive cluster of galaxies, its path bends around the cluster. Using Riemannian geometry, astronomers can calculate the spacetime curvature needed to cause this bending, and from it, estimate the total mass of the cluster. Often, the visible matter doesn't account for the bending. That discrepancy strongly points to the presence of dark matter, matter we cannot see, but which exerts gravitational influence. Because general relativity uses Riemannian geometry, it allows us to describe the universe using intrinsic curvature alone. Our universe can expand dramatically without needing any external embedding space, without expanding into anything. But as you might guess, that's not the end of the story. Just because the universe doesn't need to expand into something, doesn't mean it isn't expanding into something. After a 7-month journey across the solar system, the next 7 minutes would decide the fate of NASA's Perseverance rover. Hurtling through Mars's thin atmosphere at nearly 20,000 kilometers per hour, it appeared as a brilliant meteor streaking across the daytime sky. Suddenly, its parachute deployed and detached. A sky crane lowered the rover using long, puppet-like cords. Once safely on the surface, the crane flew away to avoid contamination. Perseverance had completed a 500 million kilometer journey and touched down in Jezero Crater, one of the most promising places to search for signs of ancient life. But that wasn't the only achievement. A tiny helicopter named Ingenuity made the first powered flight ever performed on another world. Though it was designed for only 5 flights, it completed 72. These feats remind us how weak gravity really is. Despite the mass of an entire planet beneath it, a tissue box-sized helicopter, no heavier than a bag of potatoes, could lift off and hover over the Martian surface. Yet among the 4 fundamental forces of nature, gravity remains the least understood. That's ironic, given that it was the first force we discovered, and the one we experience most directly every day. To emphasize how different gravity is from the other forces, consider 2 electrons. The gravitational attraction between them is 100 quatorticillion times weaker than their electromagnetic repulsion. That's a 1 followed by 43 zeros. This astonishing imbalance is particularly puzzling because physicists believe all 4 fundamental forces were once unified just moments after the Big Bang, later breaking apart into distinct interactions. In fact, we already have strong evidence that electromagnetism and the weak nuclear force were once a single force, the electroweak force. The rules that describe the strong nuclear force are strikingly similar to those of the electroweak interaction, suggesting they, too, may unify at high enough energies. We just haven't yet built a particle accelerator powerful enough to test it. But gravity? gravity remains the outsider. As we've seen, it's described by Einstein's general relativity, a theory that's fundamentally incompatible with quantum field theory, which we use to describe the other three forces. So if all four forces were once equal, what caused gravity to be so much weaker? One intriguing idea is called the brain-world hypothesis, a radical take on embedding space. According to these theories, our four-dimensional space-time may be a membrane or brain embedded in a higher dimensional bulk. The term brain is short for membrane. To picture this, lower the dimension. Imagine an ant crawling on the surface of a floating soap bubble. The ant lives on a two-dimensional surface embedded in a three-dimensional space. Likewise, we may live on a four-dimensional membrane embedded in at least 5 dimensions of bulk space. Brain-world theories arise from string theory, a framework that seeks to unify gravity with the other forces. In string theory, subatomic particles are not points, but tiny vibrating strings. Just as you can pluck a guitar string to create different notes, the universe can excite strings in different ways to create different particles. A special class of particles, called bosons, are particularly important because they carry forces. For instance, magnets attract or repel each other by exchanging bosons. Nuclei are held together by the strong force transmitted by gluons, a kind of boson. So far, physicists have experimentally confirmed the bosons associated with 3 of the 4 forces, but they have not yet discovered the boson associated with gravity, called the graviton. If it exists, the graviton is notoriously hard to detect. But if we ever do find it, it may hold the key to one of the biggest mysteries in physics. Why is gravity so weak? And that mystery could reshape how we answer the question we've been asking all along. What is the universe expanding into? In string theory, there are 2 kinds of strings: open strings and closed strings. According to brain-world theory, open strings, like those associated with electromagnetic, weak and strong forces, have their endpoints attached to the brain. But closed strings, which form loops, are not tied to the brain. Instead, they loop onto themselves and can move freely throughout the higher dimensional bulk space. The graviton, the hypothetical quantum particle that mediates gravity, is thought to be a closed string. In other words, gravity is diluted across both our brain and the higher dimensional bulk, while the other 3 forces are confined to the brain. So, if gravity appears much weaker than the other forces, perhaps it's no surprise. It's leaking into the extra dimensions. There may be ways to test this idea experimentally. Even without directly detecting gravitons, high-energy collisions in particle accelerators like the Large Hadron Collider might produce gravitons. If some of them escape into the bulk, they would leave missing energy signatures in the data. Physicists have also tried to detect gravity's leakage in modern versions of Henry Cavendish's 18th century experiment, which measured the gravitational attraction between 2 nearby metal spheres. Normally, this force follows the inverse square law. Doubling the distance between masses reduces gravitational attraction to 1/4. Tripling the distance reduces it to 1/9. Electromagnetic force behaves similarly. But if gravitons can wander into an extra spatial dimension, say a 5th dimension, gravity should weaken faster with distance, obeying an inverse cube law. This means doubling the distance would reduce gravitational attraction to 1/8, not 1/4. To explain gravity's current weakness compared to other forces, such deviations from the inverse square law would have to occur at very large distances, roughly the span between the Sun and Uranus. Obviously, no such anomalies have been detected in planetary orbits. But as we increase the number of extra dimensions in the bulk, gravity's leakage paths multiply, and the distance at which deviations appear shrinks. With just 2 extra dimensions, deviations might occur at distances as small as 0.3 millimeters. While that might still sound large compared to atoms, measuring gravity at sub-millimeter scales is extraordinarily difficult. Still, in 2021, a breakthrough experiment measured the gravitational force between 2 gold spheres, each 90 milligrams, separated by just 40 millimeters, and found no deviation from the inverse square law. Perhaps one day we'll shrink that test down to 0.3 millimeters and find evidence that gravity truly leaks into the bulk. But even if such deviations are found, it wouldn't prove definitively that our universe is a brain embedded in higher dimensional space. Extra dimensions could be intrinsic to our universe, but curled up so tightly, they're undetectable. Confirming the existence of the bulk might finally give us a concrete answer to the question, what is the universe expanding into? Our minds imagine that the universe might be expanding into an infinitely large, higher dimensional space, a bulk we may never directly see. But there's another revolutionary idea that may connect string theory with the rules of quantum physics: the ADS-CFT correspondence. The ADS refers to anti-de Sitter space, which we encountered earlier, a universe with constant negative curvature. CFT stands for conformal field theory, a quantum theory governing particles and forces at the smallest scale. To grasp how it works, imagine a two-dimensional mosaic disk made of triangles and squares that obey anti-de Sitter geometry. In such a space, the angles of a triangle always sum to less than 180 degrees, and squares have their corners pinched. Stack many of these disks to form a cylinder. This is a three-dimensional anti-de Sitter space. At any point inside this space, triangle angles still add to less than 180 degrees. But here's the key insight. If you place yourself on the boundary of this space, your immediate surroundings appear flat. In other words, the boundary of ADS space is flat Minkowski space, just like our observable universe. This led physicists to propose that perhaps our flat, observable universe lies on the boundary of a higher dimensional ADS bulk. This is the heart of the ADS-CFT correspondence. Physics in the bulk, ADS, is mirrored by quantum field theory on the lower dimensional boundary, CFT. If you apply string theory in a five-dimensional anti-de Sitter bulk, the four-dimensional boundary behaves exactly like a quantum field theory. It's a profound duality. The laws of gravity in the higher dimensional bulk are mathematically equivalent to the laws of quantum physics on the boundary. However, several important caveats apply. In the standard ADS-CFT setup, the boundary is 4 spatial dimensions, no time. But we seem to live in a 4-dimensional universe where 1 dimension is time and only 3 are spatial. Also, while the CFT that appears on the boundary is very similar to the standard model of particle physics, it's not exactly the same. Still, if ADS-CFT is even approximately correct, it could be the first bridge between general relativity and quantum field theory. It offers a tantalizing vision. Gravity and quantum mechanics might not just be compatible, they might be 2 descriptions of the same reality, seen from different sides of the cosmic mirror. As it stands, the ADS-CFT correspondence is not a complete description of our physical reality. However, when it was first proposed in the late 1990s by Argentine physicist Juan Maldacena, it breathed new life into a much older idea, the holographic principle. A hologram on the back of a credit card may appear 3-dimensional, but all of its information is actually encoded on the 2-dimensional surface. Similarly, in the ADS-CFT correspondence, all the information about the 5-dimensional bulk is encoded on the 4-dimensional boundary. In fact, the correspondence is sometimes referred to as the Maldacena duality for this very reason. We can even lower this concept by 1 or 2 dimensions. Although our universe appears to have 3 spatial dimensions, it's possible that all the information about it is actually encoded on some distant 2-dimensional boundary. Could the entire universe be a hologram? It's an enticing possibility, one that has helped physicists wrestle with some of the most perplexing problems in modern science, such as what happens to information that falls into a black hole. Still, the holographic principle remains unverified and incredibly difficult to test directly, but it beautifully illustrates the level of intellectual acrobatics and creative thinking physicists must engage in when seeking answers to the deepest questions of the cosmos. For nearly a century, we have known that the universe is expanding. The work of Gauss and Riemann led us to Einstein, who showed us that the universe doesn't need to be expanding into anything at all. And yet the idea of higher dimensions refuses to disappear. If we ever discover them, if we ever find solid evidence of extra dimensions beyond the familiar, then perhaps, finally, we will know, what is the universe expanding into?